Hello everybody, today we are going to talk about how to construct two transmon qubits and couple that with an oscillator using the scQubit package. Our oscillator can be an LC oscillator or it can be a transmission line resonator. Let's dive in the Jupyter Notebook and see how you can do it by yourself. So the first thing that you need to do is to import the packages that you need. Here today we only need the NumPy package and scQubits, of course. Before start the coding process, let's just familiarize ourselves with the Hamiltonian of such system. So here we can see the Hamiltonian for such systems. This Hamiltonian contains 4 different terms. The first 3 terms includes the parts of the circuit that we have but not coupled to each other. The first term is the Hamiltonian of the first transmon that we have. The second one is the Hamiltonian of the second transmon that we have. And the third term is the energy term for the oscillator, basically counting that what is the mode that is occupied. And the last term is the term that contains the coupling part. You see that it has 3 parts. The first one is the G, is basically the constant that shows what would be the strength of the coupling between the transmon qubit and the oscillator. The NJ is the charge number operator that is operating on the qubit. And the last term is the term that operates on the oscillator, basically changing the mode that is oscillating. You can see that there's a summation over 2 terms here, j equals to 1 or j equals to 2, basically defines that which kind of the coupling we are considering. The j equals to 1 is indicating the coupling between the transmon 1 and the oscillator, and j equals 2 indicating the coupling between the second transmon and the oscillator. Okay, the next step for us is to make the Hilbert space. To make the Hilbert space in the coding environment, the first thing that you need to do is to actually define the elements that we have, namely the 2 transmon qubits that we have and the resonator. Here in this part of the code, you can see that we are defining these 3 terms. The first one defining the transmon 1. And you can see that these are the variables that you need to define for the transmon. If you forgot that what are those variables, you can either check the documentation. For example, here I have the transmon qubit documentation, and we know that the EC is the charging energy, EJ is the Josephson energy, NG is the offset charge, and the cutoff charge number is the NCOT. You can also check the source code on the GitHub page that helps you to not only get familiar with the variables, also get comfortable with reading the documentation in the code and see how those elements are constructed. So in future, if you have an error, you can trace it back to see what could be the source of that error. So now you can see here we are in the scQubits GitHub page. Then you're going to go to the core, and now we are looking for the transmon qubit. So let's see if we can find the transmon qubit here. Yes, so transmon.py is part of the package that define and describe the variables for the transmon. And by scrolling down, you can see here that how the elements are defined. The next thing that we want to know is the resonator or the oscillator. So get back to the core. Let's see if we have something called resonator or oscillator. Yes, we have. And then you can come here and check the variables that you have for oscillator. But if you found some part of the documentations unclear, don't hesitate to comment down the video and we try to address that issue. So now let's get back to the Jupyter Notebook. Now that we define our transmons and the oscillator, the next step is to create the Hilbert space. You have 2 options for that. One of them is to use the graphical user interface or just writing the syntax for that. Let's start with the graphical user interface. For that, you need to define the scale of your strength. Here, G is defined as 0.1. And then you need to use the Hilbert space.create to create your Hilbert space. Now here we have 3 elements and we want to define interactions between them. So we are gonna choose all 3 and then we are gonna add an interaction term. So the interaction is defined between the 2 elements out of the 3 elements. So what would be my subsystem 1? It is transmon 1. Then I define that what kind of coupling I want to have. These are different couplings that you can have. In the Hamiltonian, we had a number operator, so I'm going to choose a number operator here. And my subsystem 2 is the resonator. And you can see here that what kind of operators you can also apply on the oscillator. The strength, I want to be 0.2, for example. So I choose the G strength 2. Add hyperconjugate, I said true. And then the next step is to create your Hilbert space. Your Hilbert space is created. Now try to do that again. This time we are going to use the syntax for that. To use the syntax, the first thing that you need to do is define your Hilbert space again, but now you have the elements in the list form. Now it's time to define the interactions between the elements of your system. Here again, we define the G1 and G2 that shows our coupling strength. There are 2 ways to define your operators. You can define that initially in advance. Say operator 1 is the operator that is being done on the transmon 1, and it's going to be a number operator, and operator 2, for example, here is the combination of the creation and annihilation and being done on the resonator. You add that as your interaction, defining your G to be G1. Your operation would be operation 1 that is being done on transmon 1, and your operation 2 would be the operation 2 that is you defined before that is being done on resonator. Or you can directly write that in when you are defining the operations inside the adding interaction function. So let's create. Good. The next thing that you may want to do is sweeping some parameters. Here we are just going to show you an example of that, and the parameter that we are going to sweep is external flux. Now in this cell, the first thing that I would do is defining my sweeping parameter. So I mentioned that this parameter is going to be normalized external flux. The next thing is to define the array that contains the number or the value of the external flux, that at those external flux I want to update my Hilbert space. Then I define that what part of my subsystem I want to be updated constantly at different external fluxes. Okay, in the next part you can see that the function that shows how the Hilbert space components are being updated regarding the external flux, and knowing that you can define your sweeping action. Here we are using a parameter sweep to define our sweeping. The first line here is making a dictionary that use the parameter's name and parameter's values. We define how many counts we want for evaluation. And our Hilbert space is the Hilbert space that we've defined earlier. And subsystem info, what are the ones that we want to be updated, transmon 1 and transmon 2. And in the last line, we are using the update Hilbert space function to show that how the Hilbert space should be updated. Now we can run that. It's going to take a couple of seconds. Here we go. Now it is calculated. The next thing that we want to do is to see the results. You can use the Explorer GUI to see and plot the results. Here we are using the Explorer, and you can see the different plots that is shown here. So for the external flux to be 0, you can see this spectrum for transmon 1, wave function for the transmon 1, spectrum for transmon 2, wave function for the transmon 2, and you can see the transitions spectrum. You have different parameters that you can work with here. You can plot the matrix elements for, you can see that for transmon 1, If you want to do that for transmon 2, you choose the transmon 2, for example, and then show the matrix element for that. So there are other parameters that you can also plot, like self-care, AC Stark, and you also have the opportunity to define that how many energy levels for a transmon 1 or transmon 2 you want to have when it comes to energy spectrum and the wave function. And you can define your initial state for transition. You can choose here, I don't know why the GUI doesn't show it pretty well, but B here is for bare, like a bare states, and DR is for dress states. And you can choose number of the photons. Okay, this was the summary of how to construct 2 transmon qubits and couple that with the external oscillator, and how to update your Hilbert space and plot the results for your simulation. Let us know in the comment if you found the video helpful, and if there are parts that are unclear, or there are parts that you're hoping to be more instructions on it. On this note, this is Ali, and I hope you found this video helpful.